So this is the lesson task. I believe is 9 or 10. I can't recall too exactly, but this is the video for that, and it's going to talk about de Moivres theorem. And before I talk about de Moivres theorem, I initially had planned some ideas for the video, but unfortunately some editing happened and got cut off and whatnot. So I'm doing this from scratch again. But to start off, we have two complex numbers. Let's call them z1 and z2. Negative 1 plus 3i, negative 4 minus 4 root 3i. These are two different complex numbers. If you graph them on the real and imaginary axis, we can plot them depending on their real component and their imaginary component. We're going to still move in a rectangular form, left, right, up, and down for now. But if I plot them, I have z1 located over here, z2 located over here. If I do the sum, if I decide to add them together, which means I add them component-wise, and that means I add the real value with the real value, the imaginary component with the imaginary component, I get a complex number located over here. This complex number, if I were to draw the modulus of each of these complex numbers, so that means the distance from the center to that complex number, you'll notice it creates this parallelogram shape over here. I'm going to have the complex number in between the other complex numbers that I'm summing with. So the sum is going to live in between z1 and z2, and in particular, if I were to draw lines connecting those 2 points, you would create a parallelogram. And this is always going to be true. We'll talk more about it in chapter 9. Now, the next question is, what happens if I multiply them? I'm going to leave it as an exercise for you guys to try to multiply z1 and z2, but you can also think of multiplication on complex numbers as foiling. It's not exactly foiling, but it is equivalent. And what I mean by that is we actually have a well-defined way to multiply things, which we're not going to cover in this class, really. We're going to cover 2 different ways we can multiply it, but they're not the exact way, but they are equivalent. So the first way is foiling. If you foil it out together, we still get the same results as how you're supposed to multiply complex numbers. And if we do so, if you multiply these 2 together, you should get the middle terms canceled out, and then you get positive 4. You multiply these last term, and I believe this should be a square root 3. Yeah, this should be a square root 3. So let me go fix that real quick. Dun, dun. This should be a square root 3i. Otherwise, it doesn't make any sense. So I have square root 3i. If I multiply them together, however, square root 3 times square root 3i times negative 4 square root 3i, well, square root 3 times square root 3 is 9. 9 times negative 4, that's negative 12. However, the i's are multiplying. We're not adding anymore. We're not combining like terms. We're multiplying. So I times I is I squared, which is negative 1 by definition. That means I'm going to be adding 12. So my value is actually positive 16 for the product of these 2 complex numbers. And then if you look at this visually, if I were to decide to calculate their polar form, if I decide to calculate z1's polar form and z2's polar form, and then the product's polar form, I will notice that the angle measures are going to be the sum, or the product is going to be the sum of the 2 angle measurement, theta and phi, where theta is the angle measurement, or argument, is what they call it now, the argument for the first complex number, and then phi is the angle measurement, or argument, for the second complex number. We can't really say it's the angle measure because we're looking at a point in particular where we don't really have an angle. More so, if we treat it as an angle, we can call it the argument. So we're just going to add the 2 angle measurement, and then you can also say that the modulus will be multiplied together. So the modulus of this complex one is really large because I'm multiplying the length of this modulus with the length of this modulus. Or length of this modulus times length of this modulus. Apologize. So now, let's show that rigorously through arbitrary values. So that means without using a specific complex number. Let's say I take z1 and z2, any 2 complex numbers. Doesn't have to be the exact ones we have. It could just be any 2 ones. If I do that and I try to multiply them together, well, I'm going to turn them into polar form first. If I turn into polar form, we have the first modulus times cosine theta plus I sine theta. I'm going to call that modulus R1. The second modulus is not the exact same. It could be, but we can't assume that. We're going to call that R2. And I'm going to use a different angle measurement. I'm going to call that phi. Your book uses theta too, but that's too confusing for me. I like to use phi. So I have the modulus times cosine of phi plus I sine of phi. That's still just turning into polar form of your complex number. We've done that already. Now, if I wanted to multiply them together, I can multiply R1 times R2 because they're going to have to multiply eventually. And then I'm just going to pull that to the left side. All I did was reorganize my multiplication. That is it. Boom. And then I have R1, R2 cosine theta plus I sine theta times cosine phi plus I sine phi. This is already telling you to FOIL, so you should FOIL this ASAP. Now, when you FOIL this, notice the angle measurements are not the same. We have thetas and phi, so I will not get a cosine squared theta. I will not get a cosine squared phi. Instead, I have these four terms over here in pink. And this is very, very big. All right, and this is the inside. So I have all of this. Now, we know what I squared should be. I squared is equal to -1, so I can just turn that into negative sine theta sine phi. So if I do so, boom, I've simplified it slightly further. All right, this is all great and all, but notice that some terms have an imaginary component. Some terms are real component. We're going to combine like terms, or you can also think of this as moving all the reals to one side and moving all the complex or all the imaginary components to the other side. So I'm going to do that real quick. If I do so, I have the real components right here. Cosine theta, cosine phi, minus sine theta, sine phi. These are my real components. They do not have the imaginary component or the imaginary number to it. Whereas the other component, I can pull out that imaginary component. Let me scroll to the side a bit. If I pull that out, then I'm left with sine phi, cosine theta, sine phi. Well, this is exactly going to be by the sum of sine and sum of cosines. We can just add the two angles plus I sine of the two angles summed. And then this is the modulus being multiplied. So this is why the product of two complex numbers have the angle measures being added and the modulus being multiplied. That's how we want to view it geometrically. Now, what is de Moivres theorem? I'm going to let you know I will not give you de Moivres theorem. Do I expect you to memorize it? No. I do not expect you to memorize it. But I'm also not going to give it to you. What I do expect is you to understand and how you can construct it every single time. So how is it constructed? Well, think about this. How would I calculate a value like z to the 6th power, given that z is a complex number? Do I expect you to FOIL this 6 times? That's a lot, because if I FOIL it 6 times, I might have 4 terms multiplying 2 terms. And that's a lot of terms you have to account for. But de Moivres theorem is very nice. All it's saying to do is go into polar form. Turn that z into polar form before you raise it to the 6th power. So I'm going to turn z into polar form. Write z in polar form here. And if I turn z into polar form, we can write it as a complex number. The modulus times cosine of the argument plus I sine of the argument. Argument of z, of course. All right, and if I do so, de Moivres theorem says, hey, we can just raise this to the 6th power. At the end of the day, we're just raising it to the 6th power. So if I multiply z times z times z times z, this is exactly what happens. Z to the 6th power is z times z times z times z times z times z. Now I'm going to use the polar representation of each one of them. Well, if I do the polar representations, I have r times r times r times r times r. Remember, the modulus are being multiplied. What's going to happen to the arguments? Well, they're all the same arguments because they're all from that complex number z. They are the same complex number. So I just have theta plus theta plus theta plus theta plus theta plus I sine theta plus theta plus theta plus theta. This is going to happen 6 times in particular if I wanted to calculate z to the 6th power. So this simplifies into r to the 6th times cosine of 6 times the argument plus I sine of 6 times your original argument. Boom. That is de Moivres theorem. I don't want you to memorize. I want you to understand how to multiply complex numbers and use that idea. The modulus are being multiplied, so you're going to multiply 6 times itself. And you're going to have at the same angle measurement 6 times in a row. Boom. And that is de Moivres theorem. So if you want to look in your book, it says that if I have a complex number in the form of polar form, then I can say that complex number raised to some power k, k is some constants. It could be a fraction, by the way. K is some constants. I can express it in this manner because of sum of sine and sum of cosine, which is very powerful. If you want to divide, instead of raising it to a power, we're going to square root it or cube root it or whatnot. We're going to nth root it. And instead of multiplying by k, we're going to divide it by k. That's it. Same idea, just reverse if you're dividing. So let's do the example. 1 plus I raised to the 6th power. How would you calculate that? Well, to calculate that value, well, we're going to treat z, that complex number, as 1 plus I. That's the complex number I'm working with. I want to raise that complex number to the 6th power. So first, express it in polar form. Well, if you draw your triangle in your first quadrant, you have the opposite one, the adjacent one. That means the modulus has to be square root 2 in that case. Or you could do square root of a squared plus b squared. You can also think of it like that. Same exact procedure. So boom, I have square root 2. Now, the opposite and adjacents are equal in value, and it's in the first quadrant, so our argument is pi over 4. Our angle measurement for that triangle, beta, is pi over 4. So boom, plugged in pi over 4. Now I'm going to apply the Moivres theorem. All it says is, hey, raise this to the 6th power. I'm shocked that he got his name because of that, but that's perfectly fine. So you raise everything to the 6th power, which means that the modulus will be multiplied 6 times itself, and that the mean arguments are being added 6 times itself. So that's 6 times pi over 4 and square root 2 raised to the 6th power. Well, this is hard to kind of calculate at times. Sometimes you're not going to be dealt with easy values. If you're dealing with the square root, I would almost always suggest you represent that problem differently. So instead of saying square root 2, I would express that as 2 raised to the 1/2 power raised to the 6th power, as you see here. Why do I do that? It's so I have a power to a power and I can multiply. If I multiply, I can see that easy value, the easy exact value. And then I simplify 6 pi over 4 to 3 pi over 2. Boom. I have 2 raised to the 3rd power. 1/2 times 6 is 3. So boom. 2 raised to the 3rd power is very easy to calculate. That's just 8. So I have 8 times 0 plus I times negative 1, because cosine of 3 pi over 2, that's down here, that has an x value of 0. And then 3 pi over 2 for the sine value, that's the y value, is negative 1. And then I calculate z to the 6th power, which is negative 8i. So that means negative 1 plus, 1 plus I raised to the 6th power, that complex number, is just negative 8i. This is very powerful. I'm able to compute these large exponents for complex numbers without expanding it fully. All right, so there's another piece for the Moivres theorem. It also applies for nth root. This is the division process. Instead of exponents, where you're multiplying each other, you're going to be dividing each other, and that's square rooting, cube rooting, raising to the 1/2 power, 1/3 power, etc. So what about if I said, what is the 6th root of z equals negative 64? That is the same thing as saying, what is negative 64 raised to the 1/6 power? They're the exact same thing. This is pre-cal algebra. All right? So what you're going to be doing first, figure out that complex number, turn it into polar form. So we have negative 64. Negative 64, what is that in polar form? Negative 64 is on, well, this is mirrored, the webcam, so I guess it's on this side right here, if I'm doing it mirrored. But it's on the left side, pretty much. So in polar form, the modulus of that, that's the distance from the center, is 64. That's clear. Well, if it's on the left side of our circle or left side of our coordinate system, then that means we have pi degrees. It's completely on that polar axis, or real axis, I'm sorry. So it's pi. So the argument is pi for both. Boom. So we have that. Now, remember, modulus is always positive. It is always positive, so we can't put negative 64. Now, the next thing I do, I apply the Moivres theorem, which I'm raising it to the 1/6 power. The only difference is that because I'm doing roots instead of raising to a power, I'm going to be dividing / doing radicals or whatever. So by the Moivres theorems, I can have this setup right here. I can say that z to the 1/6 power is equal to 64 raised to the 1/6 cosine of pi over 6 plus sine pi over 6. Why did I divide by 6? Normally we would multiply. But because we're dividing, or we're doing roots, we have to do division instead of multiplication. It's the inverse property of the inverse operation, more so. So boom. And now I put this WK here because when you do square roots, cube roots, or whatever, technically speaking, you have more than one solution. unless I tell you there's one solution, or if I say positive square root, you have multiple solutions. If you square root a value based off solving an equation, you have two solutions in particular. So we have technically 6 solutions we need to account for. 6 possible solutions. I didn't just write down square root of z or 6th root of z. I said, what is the 6th root of z? I didn't specify if I want positive or negative, so you have to list both. All right? And that also includes its complex conjugate and the complex number. So I have to list all 6 solutions. So what do? Well, I know that it's pi divided by 6. To get the other solutions, I just add the numerator by 2 pi k, the rotation. That should give me the other solutions. So let's I use k as the solution number. So there's 6 of them, so you're going to see k equal to 5 in total because we count 0 as a number. So 0, 1, 2, 3, 4, 5. Plug in 0 for this, and then I will get one root out. I will get one of the solutions. So if I plug in 0 right there, I can write 64 as 4 cubed. You can do this a different way, of course, but I write it as 4 cubed. That way I can multiply the exponents together. So if I multiply the exponent and 0 plugged in k, we just get pi over 6. So boom, 3 times 1 over 6 is just 1/2. So 4 raised to the 1/2 power, that's the square root of 4. That's just 2. Boom. So I have 2 times square root 3 over 2 plus 1/2 I. If I multiply that together, if I distribute that 2 out, I should get the first solution, complex solution, is square root 3 plus that imaginary component. Boom. That is my first solution. Now, I need 6. To get the other 5 solutions, I use the other integers, 1, 2, 3, 4, all the way up to k minus 1 in particular. If I told you to find the 6th root, I'm going to do 0, 1, 2, 3, 4, 5. If I tell you I'm going to do a 3rd root, I'm going to do 0, 1, 2, 3. That's the idea. Okay? So that's the first solution. And, to find the other solutions, all you have to do is input the different k values. So over here, k is 1 in this case. The second one, w sub 2, that's my other solution. The k value is 2. So 2 times 2 pi is 4 pi. I add that pi together. That's 5 pi over 6. So that's how we're going to be doing it. Then we just need to calculate, evaluate, and that's it. And I guess it's a bit no, that's pretty good, yeah. But that's how you would find the nth roots. You have to figure out all of the possible solutions. And I use the word solutions because if you think about it, now we can solve equations with this. Now I can solve equations with the 6th power, 4th power, and it doesn't matter if they're complex numbers. So that's something to consider. And then if I decide to plot all of these complex solutions or complex roots, so if I did the nth root of whatever, and then I got 6 values, and I want to plot these 6 complex number values, well, the interesting thing is, if I plot them on the real and imaginary axis, I have this shape. These are going to be, the first solution, second solution, third solution, all of that, all the way to the six solutions, which is W5. All right, they're all going to create this circular shape. So in the real plane, you can treat this as the x-intercept. In the real plane, they're x-intercepts. In the complex plane, once I extend the real number system to the complex, I add that second dimension or second component to it. It's not the x-intercepts anymore. No, this time, your solutions, your zeros on your real axis and imaginary axis are going to create this circular shape. And that's very important. They're very, I guess, cyclic. Cyclic. That's the right word. They're very cyclic. So that's going to be it for today. I hope that you take these notes accordingly and whatnot. Make sure you read on this, and then I will probably see you guys for the lesson test tomorrow. You guys take care. Bye.